So before I talk about toric origami manifolds, let me just talk about a little bit of context. So we have, toric varieties, right? So from algebraic geometry. So let's see, an algebraic variety that contains an algebraic torus as an open subset. And we know that they can be classified by fans. Right, so that's the fan of CP2. So that's one of the objects that I want to keep in mind. And another one, which is a little bit more, well, I'm used to them a little bit more because I'm a symplectic person, or toric symplectic manifolds. And so a symplectic manifold is a 2 n-dimensional manifold with a 2 form that is closed and non-degenerate, and then you want to have a torus acting on this manifold. So let me write here. So Tn acting on M, and you want it to sort of preserve the symplectic structure, and more than that, you want it to be Hamiltonian. So basically, that means that there's this map from the manifold to Rn in this case that has some good properties. And then toric means that you want this torus to be acting effectively, so any 2 elements of the group do different things. And that puts a constraint on so the torus can't be too big. And then for it to be toric, you actually want it to be half the dimension of the manifold. Right? And toric symplectic manifolds, it has been proved that they're classified by exactly the image of this special map, this moment map. So this is also CP2. And lots of nice things have been proved about these polytopes. So these 2 things are related by the sort of, if you take these outward pointing normal vectors, then you get this fan. Okay. So have all of these nice properties about how this relates to the manifold. So for example, I know that CP2 has 3 fixed points because the polytope has 3 vertices. All right, yes. The other thing that I want to say is that for both these 2 classes, in fact, I'm going to think of smooth projective toric varieties so that they're exactly the same thing, because I know more things about these guys. So in both these cases, you have that the manifolds are, so they're always orientable. Let me write here effectively. Okay, so they're always, I should say that, yes, so these are the same classes of objects, and so there's also a torus, but it's an algebraic torus acting. Okay, so they're always orientable. The easy way to see that is if you have a non-degenerate 2 form. What that means is that the top power is going to be a volume form, so it's orientable. They're always simply connected. So that's not as easy to see as the orientable, but basically, if you take any one circle subgroup of the torus, then the moment map for that one action, for that action of that circle, is a Morse function, and the indices of the critical points are always even, and that implies simply connected. Another very nice thing is there's this 1-to-1 correspondence between the manifolds and these combinatorial objects, so the fan or the polytope. In fact, the polytope can be seen more or less as it's the orbit space. So there's a 1-to-1 correspondence between M and its orbit space. And then it shouldn't come as very much of a surprise that you can get the cohomology of M from the polytope, because in fact you can get M, but it's a little bit nicer than that. You can actually, there's a nice name for it. The equivariant the ring of equivariant cohomology is actually the, let's see, Stanley. Oh, I never know how to spell Reasoner. It's either this or EI. Reasoner. if it's the other way. I'm sorry. I hope this person is not here. Okay. So these are all very pleasant things that these two classes of manifolds have. And then there's another. So in toric geometry and topology, they've introduced a bunch of smooth analogs of these families. That was the goal of these definitions. So there's a bunch of different ones. There's Torus manifolds. There's quasi-toric manifolds. I think there's also topological toric manifolds. There's possibly more. These are the ones that I know of. And they're all slightly different from each other, but the idea behind it is that you always want to have a torus of half the dimension acting smoothly and effectively on a manifold. And then, right, there are some different flavors, and so these are actually all different. There are some things that are torus manifolds that are not quasi-toric, and so on and so forth. I guess I should say, let's see. These are, yes, Torus manifolds were introduced by Masuda, quasi-toric manifolds, Davis, Januszkiewicz, and these, Ishida, Fukukawa, and Masuda. Okay. So these topological analogs, the ones that people actually do computations for are all orientable and simply connected. There is the one-to-one correspondence between the manifold and some sort of combinatorial data that represents the orbit space. And we don't always have that this is the Stanley-Rieser face ring, but it's some ring that you compute from delta. So for torus manifolds, which are the biggest of these, for good torus manifolds, this is slightly more complicated than the Stanley-Rieser.
Delta is the combinatorial logic you were referring to?
Yes. Yeah. Which I guess replaces this polytope. But one thing that I want to note is that if the idea behind your objects is that you have a torus action of half the dimension acting effectively, then you don't really need things to be orientable and simply connected, right? You can have a circle acting on a torus or a circle acting on a Klein bottle effectively, and that's fine and it's smooth. So somehow that makes me a little bit unhappy with these definitions. All right. So the toric origami manifolds, yes, I thought it was all going to fit there, but it's not. So. Can I?
The difference in those is that they're not Hamiltonian group actions?
Cool. In the topological ones, well, they don't have a symplectic structure or an algebraic structure, so Hamiltonian doesn't mean anything. Yeah. I mean, there are some conditions, like I think that for these and these, maybe also those, they use the words, the action is locally standard, so that means that around each orbit, if you look around an orbit, there's always a neighborhood that looks like Tn acting on Cn. All right, so toric origami manifolds. So origami manifolds are an offshoot of folded symplectic manifolds. So folded symplectic means that you have your manifold. I'll draw this manifold. And instead of your closed two form being non-degenerate everywhere, you allow it to degenerate. And you allow it to degenerate on a hypersurface, not necessarily connected, but as little as possible. So the kernel is as small as possible. It's actually going to be one vector is going to be, for each point, one vector is going to be transverse to the hypersurface, and the other one is going to be pointing in the direction of the hypersurface, so tangent. And then origami means that this vector that points inside the hypersurface, you follow that foliation, and you want it to be a principal circle fibration. So what that boils down to is that these manifolds are, you can pull these pieces apart and collapse the fibers and get symplectic manifolds. So origami manifolds are sort of made of these symplectic pieces. So you still have a lot of symplectic structure, but you don't have these global restrictions. So you can also, then you can define torus actions Hamiltonian toric. So this would be the moment image of that. So again, the vertices correspond to fixed points, and then you have these special points that are just correspond to the hypersurfaces. And you can, here's an example of the non-simply connected, so it appears very easily. And for the non-orientable, oops, let me draw. All right, this is the best that I can do for drawing RP2. And the moment image, it would sort of look like this. And I'm not going to go into details about what that. It's pretty easy to understand what's going on here. It's a little bit harder to understand what's going on here, but 15 minutes is not enough. So
you draw a double line there. Is that part of the structure?
This double line is because I have sort of this sphere and this sphere.
Right, and you're keeping that as part of the structure.
Yeah, yeah. So it's not the image. It's sort of this. It's this orbit space. We call it origami template because that's the name that we came up with. So for the simply connected case, which is represented by this drawing, it's actually in the framework of torus manifolds. So that slightly more complicated Stanley-Reisner phase ring holds for the equivariant cohomology. For the non-simply connected case, this is what Tara Holm and I have been concentrating on. So we know, let's see what, we know what pi1 is. That was the first thing, because it's not simply connected, so that's sort of the first answers. Can you read pi1 from this picture? And you can. And then you can get all the cohomology groups, like nice formulas for the cohomology groups of four-dimensional manifolds. So this is Holm Pires. And then there are some other people in Japan and Korea working on this. And they've got the ring structure for a subclass of four-dimensional ones. There's lots of them. Let's see. Eisenberg, Masuda, Park, and Zhang. So I'm hoping that at some point we can meet them, because I think that would be a really fun party. So the goals for this semester, so the first one is it would be really nice if we could get the, well, it doesn't really matter if you put the equivariant here or not. It would be really nice if we could figure out the equivariant cohomology ring in general for all dimensions. It would also be really nice if we could find some other invariants, like the Chern classes in dimension 4. Then that gives us the cobordism class, for example. So these things that we compute for symplectic things, it would be nice to be able to see if we can compute them for these things. And then the non-orientable cases, we haven't even started thinking about that. I don't know that we're going to get there this semester. Another goal is to learn some toric geometry and topology, and then sort of solve this insatisfaction that I have, that there's no flavor of these objects that includes all these examples when they can clearly be represented so nicely by a combinatorial object, and information can be obtained from that combinatorial object. So that's another goal. And then see if these things that we have can be pushed to those topological analogs without the underlying symplectic structure. So that's it. Time's up.